Okay, I've started recording. Now, if I go to Lou, I should be able to make you into the oops. Sorry. Make host. Do you want to change the host to Louis H. Kauffman? Yes.
Okay. Right. Okay, now I'm recording. And here goes the share screen. And maybe my slideshow is still up. I thought it was around here somewhere. There it is. Okay, here we go. So I'm going to start talking again at this point. You will find when you look at the recording that I went back to Temperley-Lieb algebra and talked about it again, and about the statistical mechanics models. So let's begin at this point. So these are Reidemeister moves for knot diagrams that have been arranged with respect to a direction, in this case, the vertical direction in the plane. And a diagram is said to be Morse if every horizontal line in the plane intersects the knot diagram transversely in a collection of points, or it's tangent to it at a point, maximum or minimum, or it goes through the center of a crossing. And this means that there are certain extra singularities that occur. Namely, you could have a vertical line which goes straight down through a maximum or straight down through a minimum. And so we need to add number 4, which is going across that singularity from one Morse diagram to another, swing move, and its correspondent one for a minimum. And we have a vertical version of the 2 move, as you see, and we have cancellation of maxima and minima. You can then verify some things. For example, you can verify that a horizontal 2 move is a consequence of these moves by using a swing move and a combination of the other moves. So these turn out to be a sufficient set of moves for handling Morse diagrams up to regular isotopy, which means second and third Reidemeister moves, and I do not insist on invariance under the first Reidemeister move. And one can then use this as a kind of generalization of the theory of braids to interface knot theory with algebra in various ways. The basic algebra that you are interfacing with is a category because you see once diagrams, including tangles, are written this way, then they can sometimes be composed because you'll have different numbers of ends at the bottom and the top. And that sometimes composition becomes the structure of the tangle category. And then from the tangle category, one can get lots of different kinds of invariants by taking functors from the tangle category to other categories. And what I'm about to talk about is the concrete aspect of that by assigning specific matrices, or first abstract versions of those matrices, to the local parts of the diagram, and then taking their compositions to form invariants. Anything that I do of this sort will go back then to making the matrices, or asking the matrices that are in the functorial image of this tangle category, asking those matrices or linear transformations to satisfy the image of the Reidemeister moves. And one can go further, not just linear functors, not just functors to linear transformations of modules or vector spaces. One can use the same idea and go to categories associated with a Hopf algebra. And I will talk about that later on. And then we get other ways of forming invariants. Okay.
Lou,
Yes.
what do you mean by quantum?
Content?
Quantum.
Quantum. What do I mean by quantum? Let me digress for a moment and talk about quantum, as long as you ask the question. This will take a little time, but it's probably worth mentioning as long as we're talking about the word. Let me get a blackboard to write on, since I didn't include at this point a description of the elements of quantum theory and why quantum has to do with any of this. Sorry, I'm looking for the black there. Okay, there we go. So we'll use the whiteboard. So I want to give you a very short description of how quantum theory works and why one would use the word quantum in relation to these invariants. So now I'm just going to be giving you a somewhat abstract sounding description, and then we'll make it more concrete. But in quantum theory, you have the following situation. A state of the physical system. Why is something making little bell-like sounds?
Oh, perhaps somebody wants to enter.
Ah, I see. The state of the physical system is represented by a vector. Maybe you can read my handwriting. I'll try to write carefully and it will go more smoothly. A vector psi belonging to H, where H is a Hilbert space. If finite dimensional, this means a complex vector space with inner product like this. Maybe I have a basis. Now I'm using Dirac's notation, and I'm going to assume that you have a little trouble with this once you see how I'm using it. This means a vector. When I turn it around and write it the other way, it means a covector. What's inside the bracket is just a label, any label you care to put. So you can write elephant or your grandmother or ice cream, anything you like inside there. It's just a label. And you might have a string of labels or whatever you want. So it's like a subscript, but it's a variable label that you can put inside. So I could say I have a basis, E1 through En. Orthonormal. So that means that the inner product of EI with EJ is delta IJ, and now you see the covector. And in general, if I have a vector psi, just showing you a little bit of the linear algebra so we can see what calculations look like, and then you'll see why I'm bothering you with all this. A vector in general would be somebody with complex coefficients. And the covector will have the complex conjugates. And so that means that if I had two vectors, if I had another vector, V, which was W1, Wn, En, then I would have the inner product of the two, which I always write as covector times vector to think of their inner product. The inner product of the two is W1 bar, C1, plus and so on, plus Wn bar, Cn. Complex inner product. And that means, for example, that the norm squared of a given vector is the sum of the absolute value squares, the Z1 bar through Zn bar. So that's the background linear algebra that I'm talking about, and that turns out to represent a state of the physical system. Now, 1 second. Okay. Yeah. Now, okay, so let's go on to the next slide. Now for the physical interpretations. EI corresponds to one of many possible observations that you can make. So you may be you may be thinking of some nice quantum situation, like there's a screen and there's a double slit, famous experiment, right? And there's a source of electrons here. These electrons are thought of as wandering about and going through a slit and ending up somewhere on the screen. In this case, screen can't be misspelled, right? In which case there is the points on the screen in some interval. So this point X would belong to an interval A, B in our one-dimensional picture here, where A is this distance, this point on the screen, and this is this point on the screen. And then the basis that I described to you would be in one-to-one correspondence with the unit interval, AB. and we would have a huge set of possibilities. It would be uncountable, but we could do that, and we could think of having the basis being the set of EX, one for each possible result, which would be the result, the observation would be electron seen at such and such a point. Of course, you could choose a subset of the interval for the purposes of your experiment, like dividing a ruler, and then you would have a finite number of elements, and those would be the basis that you were working with. But observations, possible observations. The possible observations are then what you're interested in from the point of view of doing an experiment. You want to know, did I get this one? Did I get that one? When you do an experiment, measurement, takes the state of the system to some observation. So you start with this vector and you end up in one of its components, and then the Born postulate, Max Born, the Born postulate is that the probability of getting this observation, that's what I mean by the probability of an EI, the probability of finding the electron here is equal to the coefficient squared in psi. Remember, psi is equal to the sum on I of Ci times EI. So this makes the quantum theory into a probability theory. And you see that this is not an ordinary probability theory in that the coefficients here are complex numbers, but it is a little like a probability theory in that the sum of the absolute value squared of the EIs, that's the norm of the vector, we will assume it's equal to 1. And I neglected to say on my previous slide that we assume that the observed psi, or just the psi, never mind that observer, let's forget it. We will just assume that the psi that we're using for our information purposes has norm 1, has psi star equal to 1. That just means that the sum of the absolute values of the Zi squared is equal to 1. So you see, the absolute value of the Zi squared is a candidate for being a probability. It's a number between 0 and 1. But the states themselves contain more than the usual notion of probability. If I wanted to formulate probability theory for casino purposes, I could write a dice as the sum over 6 directions in a Hilbert space and take coefficients, which were the weights, the probability weights for the individual faces of the die. And then I would have a probability vector for doing roulette or dice game or whatever I wanted. But I wouldn't have quantum theory. In quantum theory, the coefficients squared are the probability. The coefficients themselves can be positive, negative, complex. And that means that when you have a probability vector associated with one event, with one situation in the physical system and another, you can add them together to get yet another amplitude, another vector. and the way the complex numbers add and subtract from one another can model interference phenomena in the physical situation. So the thing that you're finding that you model here is the fact that you can have many pathways that take you here, and then the final amplitude for starting from the beginning here, you would like to know what is your probability of starting from the beginning and ending up here. To each one of these paths, there is associated a certain complex number, and you add them all together and get this. This model encompasses that idea of adding up to get an interference. And so I have told you how to measure and how it comes out as a probability, which is the sum of the absolute CI squared. I need to tell you one more thing in this short course in quantum theory. So what do we have so far? We have that the vector is in our Hilbert space, which we'll take to be finite dimensional. That measurement takes the vector and sends it over to one of the basis elements. That's the measurement basis with probability equal to absolute ZI squared. And of course, you can write that as an inner product with EI and so on. I won't worry you about that. And then thirdly, process, physical process. Process is a unitary transformation. U taking the Hilbert space to itself. Now, unitary means exactly that that the norm of the unitary transformation applied to psi is equal to the norm of psi, the length of psi, which is the square root of psi. So this just means that lengths are preserved. It means that if you have here the sum of the zi squareds is equal to 1, then that means that the sum of the zi prime squareds is equal to 1 after you applied u. And if u is a matrix, then that it corresponds to u star is equal to the identity, where u star is equal to the conjugate transpose of u. So that's the whole story. That's quantum theory. Physical processes are now you'll notice that preserve the probability distribution, right? Oh, I'm sorry. I meant to say the absolute value squared is equal to 1, of course, right? So you have associated to the psi a little probability distribution. The probability distribution are the absolute squares of the zi's, and the sum of them is the length of the vector. The length of the vector is preserved by a unitary transformation. The unitary transformation is generalized rotation. It preserves the vector lengths. And so it takes a probability distribution into a probability distribution. And that's what a physical process is. So when you have a quantum process, that's what's going on. That in the model of it, the vector that represents the state of the physical system is rotating and landing on another vector, and that's a complete description of what quantum theory is at the level of this. What's missing, of course, is how do you get this unitary transformation? And I'm not going to talk about Schrodinger's equation and the Hamiltonian and how knowing about the energy in the system and so on gives you unitary transformation. That's where a little more physics comes in. But for those who are interested in understanding quantum algorithms, this is almost enough. You can start looking for ways to formulate mathematical problems in terms of this framework. Now, given that this is the framework, what does this have to do? What could this have to do with knots and links? Let's think about it. Let me tell you what Yang, C.N. Yang, what kind of a model C.N. Yang was using that led him to the Yang-Baxter equation. So Yang is thinking about a toy model where you have one dimension of space and one dimension of time. And so you can draw pictures of physical processes by drawing a plane where space goes this way and time goes this way. And you have some particles. And these particles have labels, let's say spin A and spin B, and they interact. And they end up with different spins up here, A prime and B prime. And let me just put a little blob there. It's not meant to be a knot crossing for him. But we have this directionality and it looks like a crossing. And you would like to know what is the probability amplitude for this process. And you would write that as a certain number, A prime, B prime, A, B, belonging to the complex numbers. And that means that the probability would be the absolute value squared of that number. Okay. Now, what would that look like in the quantum model that I was just telling you? Now you begin to see the answer to the question emerging, I hope. That if maybe I should just speak informally before I do some formalism. You see that this looks like a knot crossing, and that Yang is concerned with something that diagrammatically looks a bit like knot theory. He's going to be thinking about multiplicities of particles interacting, maybe 3, and they wander around and interact in some way like this. Yes, I don't know if bits of things obscure the screen, but they do for me, and they may not be visible to you. I don't know. It doesn't matter. Just getting them out of the way. That's why you see me sliding things up and down a little bit. But here's a more complex interaction, right? In this case, you have particles A, B, and C going to A prime, B prime, C prime, and then in this case, B and C interacted, landing here, and then A interacted with the new B to produce the end B, A, B, and C. So there were 2 interactions in that order. And what is now the probability amplitude, I didn't write it in the previous slide. The probability amplitude is that complex number whose absolute square is the probability. So there are two things that you can see now. You can ask, well, what then would be the rule for the probability amplitude of two concatenations of processes like this? That's key. What would the probability amplitude be for this? And the answer has to do with the fact that we're going to be multiplying matrices, because there are intermediate positions here. This is still A, but this could become I, and that could become J in the interim, right? And I claim that the probability amplitude for this concatenation of processes is just going to be the product of the matrices where you sum over this index, which is the index between one matrix and the other. What matrices, you say? Well, let's go back to the quantum model. There is a basis of things A, B to begin with. Those are the particle states you started with. And you ended up in particle states that were represented by the other possible observations, which are A prime and B prime at the other end of our little process, right? And there is this unitary transformation, which I'm going to just call R, which takes us from one situation to the other. And R applied to, I'm going to stop writing commas, R applied to an AB is going to be equal to some summation on I and J of R I J A B Ij, the upper possibilities. This equation expresses the probability amplitudes for starting in AB and ending up in somebody up here. You don't know what you end in up here. This is all the possibilities, and these are the complex numbers that correspond to those possibilities. The Hilbert space is now spanned by the double indexes that correspond to the beginnings, the preparations, and these are, other elements in the same Hilbert space, all possible spins. And this coefficient is now the probability amplitude. And now let's go one step further and figure out what will happen if we concatenate two processes. So if I concatenated two of these processes, I would be looking at this. I started in A and B, and I could end in the middle in some I and some J, and then I end up at the end in a C and a D. And I claim that the amplitude for this, remember, the amplitude is that complex number whose absolute square is the probability of going from one thing to another. So I want to know that complex number. That amplitude is going to be equal to the sum on I and J, all possible intermediate things that can happen, R lower AB upper IJ, R lower IJ upper CD. And this is because R of a vector xy is equal to the sum of R lower xy upper ij ij. That's our unitary transformation. Unitary if quantum, if really quantum. And this is where what we do in topology is not always quantum. The R matrix for the scattering process would be a unitary matrix in the vector space spanned by all the spin pairs, if we were doing quantum theory. But as you see, this gives a rule for combining matrices by summing over common indices, and you can think of it as indeed the matrix. This is, I'm sorry, I'm getting ahead of myself, but if I were to compose R with itself, then you would see that the coefficients of the composed matrix are exactly this. That's just the linear algebra of composing the matrices. Not to bother you with that. The rule is just like the usual rule for composing matrices, where the start index is here, the end index is here, and when you multiply two matrices, you sum over the middle common index between the two. All right? So that means that we know how to get the amplitudes for the concatenated processes. Now, Yang is wanting to understand concatenated processes of these type for finite dimensional matrix systems. And he understands how complicated that algebra gets to be, and Yang decides to assume that the processes only depend on the underlying permutation. Sorry, my handwriting is getting illegible, but there's an underlying permutation. So if for example, I started with 3 points and I ended it with 3 points, and from the point of view of these strings that I draw, which cross through one another, the process looked like this. And maybe I'll have another one right there. Then I have the permutation which is 1 goes to 3, and 2 goes to 2, and 3 goes to 1. And that has the same permutation as this. Same underlying permutation. From the point of view of the way the processes go, it's quite different. The first two particles interacted, then the second two, and then the first two. Here, the second two interacted, and then the 1 and 2, and then so on. But from Yang's point of view, he wants these to have the same. Now, in what sense do they only depend on the underlying permutations? He doesn't mean that the physical processes are different. He assumes that they have the same amplitude. If you were to write down what it means to have the same amplitude, you get the Yang-Baxter equation. And so, one reason why we're calling these invariants quantum invariants is because they actually look like quantum amplitudes in the sense that I've been describing to you. But the amplitudes are not necessarily complex numbers anymore. We let go of that part. We keep everything but saying that they're complex numbers. And then they could be elements in a commutative ring. They can be all kinds of things. And we have more flexibility for finding the data that we need in order to make them into invariants. I think I want to continue writing the slide for a minute. So we could follow Yang's point of view and write down the terms that correspond to the Yang-Baxter equation by following the prescriptions for multiplying the matrices, you see. So if I started with A, B, and C here, then I end up with an I here and a J here, and this is still a C. And then I might have a K here. And these are my outputs, which I'm calling A prime, B prime, and C prime. And now I'll call these I, J, and K, but they're dummy indices. They aren't meant to be the same. We're going to sum over those. Those are the ones I'm going to sum over, and these I'm keeping fixed. So from this point of view, I'm simply composing some linear transformations. And as you see, from the point of view of linear algebra, if you take the interpretation, which maybe Yang is understanding, but probably writing everything out in matrices. But everyone who works with this understands that putting an extra line corresponds to a tensor product. And so what you're looking at here is R tensor I at the bottom in the left-hand part. And then you have an I tensor R in the next level. And then at the top, you have an R tensor I. And in the second one, these being equivalent, in the second one, you have an I tensor R at the bottom. And then you have an R tensor I. And then you have an I tensor R. And so this tensor equation, the composition of these equals the composition of these, is the Yang-Baxter equation. I should write simplified because in point of fact, if you go back to the physics papers, they have some other parameters that they're keeping track of, not just the amplitude for spins. There might be momenta and other things in the brew. We'll come to that, maybe. But there's the Yang-Baxter equation, and in indices, you see it says R upper ij lower ab. You just write them down, one for each of these crossings, and you get the Yang-Baxter equation in indices. R upper ij lower ab, R upper k c prime lower jc, R upper a prime b prime lower ik equal to R upper ij lower bc, R upper a prime k lower ai, and R upper b prime c prime lower kj. Fine. Summed on I and j. Summed on I and j. And it is a long-standing convention that people like to use, that whenever you have repeated indices, you sum over them, which is exactly the same. IJK, sorry. I heard a rustle there, yeah. Summing on IJ and K. You're summing over all repeated indices, and that means that you're summing in the terms of tensor diagrams like these, you're summing over all the internal indices in the tensor diagram, and you have left the outsides fixed. Now, another thing to notice about this equivalence of equality of amplitudes is that from the point of view of statistical mechanics sums, which we were talking about before, this is a statistical mechanics model where the vertex weights are happening in relation to the nodes here, these nodes. I have more than one kind of node here. I have index label nodes, and I have the serious nodes of the particle interactions. So you have a four-valent graph, and at every point in the graph, you have a vertex weight, Rijk, here. And you're taking the sum over the products of all of them, summing over all the different spins in the system. Well, that's just like the abstract statistical mechanics model, not particularly having to do with space and time, more just graphical. And that's the way in which Baxter comes to the same relation. Baxter says, I have a four-valent graph underlying my statistical mechanics model. I have weights depending on four spins at each vertex of the graph. And I wish to simplify the terror of my calculations by assuming that this switch will be present. And so he investigates the same underlying linear algebraic structure as Yang. And so this equation gets around and turns out to be applicable to a lot of different physical situations. And that's why it's called the Yang-Baxter equation. And continuing with our quantum idea here, let's see what happens when you try to formulate this in terms of knots and links. So if you started with a knot and tried to look at it in this way, the knot tends to have some features that weren't directly in Yang's picture, although they could have been. And I don't think Yang had creations and annihilations, but we could go back and look at his paper. You see, what happens if you have a knot is you also have this, which looks like a creation of two particles, and you have this, which looks like an annihilation. I can't spell. Now that would give rise to a matrix element, and this gives rise to a matrix element. Here you have M upper AB, and here you have M lower AB. I'm not worrying about orientation. And this would be the probability amplitude for the two particles to be created. Now, the thing you have to understand is that now I don't necessarily have the ability to say that this is unitary, because I'm going to be going from one dimension to two, or I may be going from the complex numbers to some vector space here. And here I may be going from the tensor product of some vector space with itself, let's say tensor product, back to the complex numbers. So these are not necessarily unitary, creations and annihilations. But I can still have the idea of a probability amplitude such that the absolute square of this is equal to the probability of finding these particles. So these can be added in. But these guys need to be unitary if it's going to be quantum. And then we would have a similar diagram to Yang's, but we also need one other discrimination. We need to discriminate between this guy and this guy. So there's going to be an R, and there's also going to be an R bar. And of course, for our purposes, we know that R bar should be equal to the inverse of R. We know that, because after all, you have the second Reidemeister move. So we have R bar is equal to R inverse. In Yang's situation, he had that it was independent of permutation. And so this would have been equivalent to this. And Yang's R would be squaring to form the identity in his situation, Yang. So he would be looking at solutions to the Yang-Baxter equation that squared to the identity. He would be looking at permutational solutions. But Baxter does not assume this, okay? Baxter does not have to assume that his vertex weights are squaring to the identity, and so he's closer to the knot theory situation. And there are many physical solutions to the Yang-Baxter equation that can be used to make link invariants. Now, how do you make a link invariant? Well, by the same method, I can put low internal indices into this process like this. And in fact, you can ask, how many indices do I need? If I think categorically of it as a composition of elementary morphisms, and I can, and it's a good idea to think that way. If I think that way, then my elementary morphisms are cups, caps, and crossings. And I can think of composing things that way. But if you're looking at the combinatorial form of the picture as a Morse diagram, then what you can do is you can say, I have critical points. Here's a critical point. And here's another critical point. And I'm going to put one index thought in between every two critical points. And that's a sufficient number of indices to mark it out as a process. Then you will have marked out a cup here. You will have marked out another cup here. You will have marked out a crossing interaction here, and so on. And so that's the minimum number of indices I need. Let me write I, J, K, L, M, N, O, P, Q, and R. And then you can read the amplitude for going from the vacuum, in the sense of physics, to the vacuum. The amplitude is this composition, which is a scalar because there are no free ends. So that's going to be, and we can read it easily, and we don't want to write it out, M upper OP, M upper QR, M lower IJ, M lower KL, R upper IJ, lower OM, R upper KL, lower NR, and R bar, upper MN, lower PQ, summed over all the indices. That would be the partition function that would give the probability amplitude of going from the vacuum to the vacuum. And that would be the quantum invariant of the knot if we made the right assumptions about the R and the M. And what further do we need in order to do that? Well, we need the Yang-Baxter equation to get the third Reidemeister move. We need the analog of this that I just erased to get the second Reidemeister move. So the one extra thing that we need in this formulation is this equation, and it's flip. And you see, if you look at this carefully.
Lou?
Yes.
Yeah, by flip, you mean that the arch should go under.
I just mean that you could write this as well. I also mean you can change crossings, but I mean, you know, this. And if you're careful, you can deduce one from the other, but I'm just pointing out what's needed.
Yeah, but the important thing is you need to change the crossings.
Sure. Whenever I write a move of a Reidemeister move type, it's always understood that there might be another case where all the crossings are switched.
Okay.
Yeah. But look at one of them so we can focus. And what you see here is an R bar. And here you see an M. And here you see an M and an R. So when you put in the indices, you get something R bar M with some indexes connecting them and MR on the other side. Or another way of putting it is the following. That if you have this little wiggle in the middle and the R bar in the middle, then you see that you have M, and then you an M upper, and then you have an R, and then you have an M lower. So I'll just write it without indices: M upper, R, M lower on this side, and here you have R bar on this side. So the inverse is obtained by way of the M's with indices appropriately placed, right? Yeah. Question? I thought I heard a question. So in order to satisfy the Morse moves, you need that the inverse of the R should be related to the cups and the caps in a certain way. And of course you need that the cups and the caps should do each other in. And that means something very simple. It says there's an index here, and an index here, and an index there, and an index there, and an index there. I decided not to write on another board. And then you have M lower AI, and then you have M upper IB, summed on I, and that should be equal to delta AB, which is just going to be the Kronecker delta, because you want a little edge, which doesn't. So what does that say? That says that the lower M is the inverse of the upper M. And so you need a solution to the Yang-Baxter equation, and you need some augmentation of it with matrices M that will behave correctly. And you can often make this. This is very similar to making a Markov trace for the invariant using the braid group, where then the Markov move becomes an extra piece of algebra that has to be satisfied in order to get a link invariant. It's also of interest to compare this with the Markov trace. You can put this in braided form and examine what it's saying there. But this is all in relation to the question, why do you call them quantum link invariants? And I say, at least I call them quantum link invariants because they are quantum amplitudes generalized, where they really would be quantum amplitudes if the matrices, if the matrix R was unitary and we were thinking of a physical model in that form. And indeed, one can look for unitary solutions to the Yang-Baxter equation and think about this for quantum algorithms and quantum computers. So I'll go back to the slideshow now. I hope that answers the question a little. Comments on that before I go back off the board?
Maybe one more thing, the irreducible representation V, the two-dimensional representation that you use in the bracket is the same as the two-dimensional representation for spin 1/2 particles.
Yeah, that takes us off in another direction, but it's right. Worth mentioning that that you would be, if you're doing the quantum theory, you would be thinking of at the very beginning, you would be thinking of the unitary group, um, or you would be thinking of the special unitary group, and you would be discussing spin of particles. And what happens when you go over to, when you look at what is the analog turns out to be SU2Q, where Q is a parameter, might be square root of A in our terms. And this is the quantum group. Which isn't a group anymore. It really corresponds to a deformed Lie algebra. And there is a corresponding Q deformed theory of spin. And the Jones polynomial, the bracket, corresponds to the lowest dimensional irreducible representation for the SU2Q. So the physical analogy continues in that way, and then one also has spin interactions. So you can have a particle of spin A interacting with a particle of spin B to produce a particle of spin C, and this in the physical side corresponds to taking a certain representation space, tensored with another one, and projecting it to a third. And one has combinatorial versions of this, at least in the Jones polynomial case, that are easy to work with, and so one can add trivalent vertices into the system and have invariance of links and knots with labels on the edges that correspond essentially to the number of strands and trivalent vertices like this, and that corresponds to the theory of colored Jones polynomials. So the theory of colored Jones polynomials, which comes up in many instances, and is a whole raft of invariants that are all related to the Jones polynomial, have to do with taking that lowest dimensional irreducible representation and taking tensor products with itself. And it can be understood without going into the group theory, or you can use the quantum group theory. But quantum link invariants are correctly described. The shift away from quantum is only in the sense of letting go of unitary. Not too bad a misnomer. Quantum groups are a big misnomer of the usual kind that one has a tendency in speaking in these realms to conflate the group and its Lie algebra. They're really deformed Lie algebras. It's very interesting to see how quantum groups are related to the bracket. I could come back to that, and we can see how you can construct this by having the right thoughts about the bracket state sum. But maybe another comment, as long as I'm making these comments. This is I'm not meant to be very intelligible unless you saw these things before, but we can go into it. But I think this categorical remark is very interesting philosophically. What happened here when we did this is that we started with a knot or a link, and we made it into a Morse diagram. And then once we made it into a Morse diagram, the knot corresponds to a morphism in a category, right? It goes from one place to another. It goes from the vacuum object to the vacuum object in the thing that we're looking at. And then the functor takes the category to let's say, to vector spaces, and so the morphism becomes an endomorphism of vector spaces, and we measure the endomorphism and find an invariant of the knot. So the space turns into a morphism and thereby becomes measured. And that move is not one that a classical topologist would have thought of. It's somehow out of range. And then the next moves that occur after this are perhaps even less obvious, that you would turn the knot not into a morphism, but you would turn it into a category, and then you would measure the category. And how much farther does this sort of thinking go? I'm referring to the next stage of things where the knot turns into a category, and you do something like measuring the cohomology of the category with some appropriate coefficients, and you get link homology. At least in the Kovanov case, you can describe it that way. How far does this sort of extended thinking take you in terms of understanding basic topology? That's the question. So it's still in this quantum realm. It's in this quantum realm that things were getting transformed that way conceptually, out of ideas coming from the physics. So now I'll stop the Blackboard work. I'm recording this so I could rewrite the slides a little bit and add them to the slideshow. And rewrite these scribbles and add them to the slideshow a little bit. Okay. So are we now at the end of our time? Almost, aren't we?
Yeah, somewhat over actually, but anyway.
Well, this is maybe a good place to stop and give you a preview. So I'll just take a couple of minutes. If you look at the slideshow, which you have as it stands, you see that I went through this a little more formally without the background talk about the quantum. So that's what I did. And then I wrote down a particular M that gives the bracket. And it's off of this particular M that gives the bracket that we can take another extension here and see how the quantum group appears. I think I'll do that. And then I also told you last time how taking another abduction by letting the size of the matrix change, but the pattern remain the same, that you end up with more solutions to the Yang-Baxter equation. It's a lot of fun to verify that this is a solution to the Yang-Baxter equation if you're willing to do it by diagrams. it's also fun to just put the matrix into Mathematica and check that it satisfies the Yang-Baxter equation, but kind of more fun to do it by hand. And then, oh, yeah. Then I wish to point this out, and then we'll more or less quit. If you take that form of matrix that I wrote down, where less than means the indices are less, equals means the indices are equal, and not equal means the indices are not equal, then its inverse is obtained by flipping in the way I just did with a Q and a Q inverse. And if you take the difference between row and row inverse, you land up on Q minus Q inverse multiplying the logical possibilities of less, greater, and equal, which are all the logical possibilities between two arcs that go near one another. So that's just the identity. And so you get R minus R inverse equals Q minus Q inverse times the identity. And we connect with Roger, who was telling us about the Hecke algebra. And that's saying that rho satisfies the Hecke algebra identity, which can also be thought of as the Skene identity. And of course, there is some framing involved. This gives a model for the Humphrey polynomial. And in fact, I will go on and tell you, not in complete detail, but in summary detail, how it does give you a model, a state sum model, somewhat like the bracket for the Humphrey polynomial specialized, by expanding it like that, you see, with some stipulations of less, equal, or not equal, and evaluating the loops correctly, and evaluating loops with logical conditions between them correctly. So this is one way to get a proof that the Humphrey polynomial exists and to see it as a state sum. We'll talk about that. And I'm skipping slides because we're going to go over this in a little more detail next time. Then I'm going to talk about the piecewise linear version of state sum models, which is quite fascinating and again related to some models that physicists use, where you keep track of the angles between the lines. And then instead of having weights at maxima and minima, you have weights when something changes its direction. So that's what it's going to look like next time. And as long as we started talking about the meaning of quantum theory in relation to this, we can continue talking about that as well. I'll stop here.
Oh, thanks, Lou. That's great. Yeah. Are there any questions?
Just an observation. I believe it was in 1987 at the Isle of Thorns where Tureyev presented the combinatorial solution that Lou gave.
The combinatorial solution that I was showing you just a moment ago with the R matrix for the Humphrey.
I believe I saw Tureyev.
Yeah, the earliest appearance of that is due to Jones at the same time as Tureyev. Jones wrote a letter showing how to do that state sum and sent it all around, right around the same time that Vladimir wrote his paper on the Yang-Baxter equation.
Dale and Roger and I think, were at that conference. I don't know anybody else in this seminar who was there. Dale, were you there?
Dale, you need to be, you've been muted.
Okay, yes, I think I was there.
Well, that was that in the 70s or the 80s? I think
80s, of course, yes.
Yeah, right.
None of this happened in the 70s. But it's interesting. I mean, the Yang-Baxter equation stuff, that happened in the 70s.
Yeah.
And then as the 80s started, Fadeev and Reshetikin and Takhtajan were doing a lot of analysis of what kind of algebra should be related to the Yang-Baxter equation. And then Drinfeld got into the act along with Jimbo and other Japanese researchers, and that's where the relationship with quantum groups emerged.
Living history. Okay, well, if there are no more questions, I'll just thank Lou again. And the next talk will be on Friday. And I'll be talking about old school three-manifold theory. Just for a change, but it's needed. So see you then.
Thank you.
Thank you, Lou.
Thank you. Thanks.